Yes. Okay, so good. Yeah. Today's date is the 30th of January. 30th of January is this. Time now is 5:39 a.m. 38 a.m. Let me just open a new document. Yeah. So this is basically in SIGI. The title of this video is, as you see it, basically SIGI order should go along like NSIGII Trident package verification via bipolar Cisco order and chaos separation system. Create, destroy, renew, repair, build, break things. Okay. So what is clear today, but just tonight. So let me just start with the kind of what we did today. Here. So the board, you can see the board here. You can see the board in space. You have the space around the board. So this is me. So we will start. So we're going to do a diagram here, but it's all biological. So this is a biological diagram here. Uh, so you just do diagram. So if you remember the nine, if you can, rebuild something, you can re-break it. Because this you can do some. If you do something, you can break it. If you can create something, session, a message, a template, something, you can destroy it. You can destroy it. If you can do something, you can break it. You can create something, you can destroy it. If you can, basically, you can break it. If you can repair something, you can renew it. But this model is basically the title of what's title here. Chaos order separation concern. These three things what an enzyme does, like saliva. Saliva can so if you have why this works, model works because of data model. But the problem with this model is you have to have something isolated. For example, an enzyme, a saliva enzyme doesn't have a nucleus. Saliva itself, like my spit, does not because saliva does not have a nucleus. It just so it's not it just does perfectly. It doesn't need any more nodes. So the replication just there's no nuclear in saliva. It's made by another some protein in saliva glands. So the example because saliva can break food down. Saliva breaks food down, keeps breaking food down, keeps breaking food down. It doesn't rebuild itself because it just collects. It just get reproduced by saliva glands, and the saliva glands in your esophagus from the esophagus to your from your esophagus, which is your esophagus, your tonsils. So after the tonsils, your esophagus, which is your diaphragm, which is your voice comes from. So your diaphragm, you get your esophagus, and then you get your saliva released somewhere in there. Because in the villi of saliva gland. If I remember, this is villi. Saliva doesn't need to doesn't break itself in structure. It's only rebuild itself. By rebuilding itself, it just collects more saliva to solve the problem. It doesn't take more saliva and it doesn't need to. So it just has a nucleus, or one nuclei. It doesn't have a nucleus, and that nucleus will be able to multiply. And saliva does not multiply. It does not multiply. It just grows at a steady, constant rate, and that constant rate is not exponential because you cannot. It's not a cell. It's not a cell. It's saliva. It's not a cell in the body. It's a cell, yes, but it's not a living organism. But it does the job as a clear system. It's not a conscious organism per se, but it's not a cell which can divide and make purpose. And cell can create a system, but the cell can only rebuild itself. So rebuild itself, and you can break stuff. So another can break stuff, but not itself. It can break things food product itself, but not itself. It cannot rebuild itself, rebuild food structures. It cannot break stuff. So if I process to rebuild out the saliva, and causes to break, if I cannot rebuild, what can I do? If I cannot rebuild myself, I cannot repair myself or renew myself, and I cannot create. So what I can do is destroy. And this is said, this is so see this diagram, it's all a diagram. And what is a diagram? A diagram graph. And you're trying to have a message that respects this principle of break and review, create and create. You have two crates, you have one destroyed. That's it. But the system has to verify itself of the kind of preparation it's doing at that specific point in time. At that specific point in time. So how this works, mathematically speaking, is order and chaos. Is there order in the system or is there chaos? So two sides of the equation. So I'm looking for potential equation. Something defines some kind of a spring and so you get the equation of the system. You get if I want to create and destroy it and send a message, what am I going to do? I want to show you two sides. So you have two pole sides, order or chaos, which has two sequences of instructions to run. Order and chaos. Order refers to is the system coherently ordered? Is it working against itself? Am I going to will this program crash? Instead, it's a really trying packet. And the beauty of this is that order is order. If you get order, you get chaos. So you always check chaos for order. Just by observing the dimension of order and chaos where the program was running. For the protocol. So this is a BIParite system. BIParite system that knows what it's doing via observer and conscious. It knows what it's observes and then consumes. It observes then act. Well, it's going to act in order, it's going to act in chaos. So if order means building stuff, breaking stuff, building stuff or creating more stuff, the system can also panic and have chaos and break stuff and lose stuff. So if a system means build stuff, create stuff, and if an order sequence is build, let's do random order. Build, repair, build, and create, repair, and build. Create, repair, and build. So, if the sequence is create, so what order? So if the order sequence is if an order sequence is if the order is renew, repair, build, and create a session, like a temporary session. If I can, so if I say take the orders, create something first, then I repair, renew, create something, renew it, build, renew it, then build it, then repair it. So I'm saying, so if an order sequence is create a session, create then, create renew. Then before it's about to break, build. Oh, so create, then so create, rebuild, create, build a new thing, repair, renew, repair, repair. Create, build, repair, renew, repair, then renew. Repair, then renew. That's it. So this order one will be, this is a create, build, repair, renew. But I want to speak, there's no matter in here yet, but this is the order sequence, this is the order of it. So then you get the opposite, which is the opposite order, which is the chaos. Chaos on the system. So you get create, destroy, so you get destroy, break, repair, renew, and repair, renew, and repair, renew, and repair. And then finally, yeah. So you get the opposite, the polar opposite on the board here. So the term creation here, so if you go to the board here now, so just go to as you can see, the chaos here is destroy, break, renew, and repair. But I'm going to go to the math now. But the order sequence is this is what you're running. And what's the video about? The verifier? That's what I'm talking about here. So I'm going to do order some. The trident packet. So because you got three messages, you go to three. So the goal is three consensus, three tridents, two packets of verification. So you have 3 or 2 mapping of the system. So the order is if the order is on, you get 2 you can also check the order. You can check the order or you can check the chaos. Checking the chaos reminds you to take two maximum. So you can take a sequence of order, or one chaos. You can tell a system of 2 orders, one order, one chaos, and two chaos, 2 C or CCO, 2 COO. This will mean that order and chaos are intertwined. So if the message is 3, you try the message, 3 messages. Okay, springs. Which is spring to this. You have again 2 orders to solve that message. So 2 orders. So the goal of this, the whole entire point per point is to express that the messages can be 512 bytes long over length space. So the goal is to have destroy, build, break. Okay. So it doesn't matter what the case is. There's chaos. When experience chaos and then order, it's almost able to fill that. So fill the flow. So mathematically, this works by spring physics. A spring verifier. The spring. Let me get my other choke. So let me do some water first. I'm feeling thirsty as hell. Oranges. So the message appears in triplets. The message appears in threes, and triplets. The triplets is basically 512 times 3. For the word OBI nexus. 512 times 3 is 1,000. 412 bytes times 3 is 1,536 bytes. And 5,132 bytes over time. So half the message will be 512 bytes divided by 2 will give you 256. 252 bytes divided 252 bytes in half the message, and double time. Double time will be 2 seconds. So you have double time, that'll be 2 seconds. 2 seconds will be 4 seconds times 4 seconds will be 1,024 bytes, bit rate, bytes per second transferred. Oh, bits per second transferred. 1,024 bits per second, no bytes per second transferred. per 2 seconds, for every 4 seconds, no, oh wait, for every 4 seconds, so per 4 bytes, which is an order. So I'm gonna start this video now. Like, how long do I have? I have time. So let me just clean the board and continue. So I'm gonna now erase this part here. I'm gonna keep this board and move it here. So, oh no, wow. Anyway, so the order operates to get we build to break on. So we get the order. Let's build. Let's build. Yeah. Yes, which is destroy. Destroy break. Destroy. Going to build. We need repair. Okay, so go destroy break, and then break and go destroy break. Opposite renew, or renew is opposite of repair. Repair. Opposite to repair. Repair. Renew. Okay, so my goal is to have this is going to work now over Cisco model. So, so go again 3 to 2. Message is try 3 to 2. So let's take another. Let's take 3 to 2. Let's do it again. So let's do 2 market. So let's do it properly again. So we have a message that's 512 bytes long divided by 3. Okay, this is 1024. $1,025 divided by 3. Divided by 3. In the best case, that would be okay. 12 bytes divided by 3. Okay, let me use my computer. 512 bytes of data divided by calculator. Let me do calculator. Shifted 3 times. So that would be a scientific calculator. That would be programming or octal binary. 512 bytes. So we have decimal. 512 bytes in decimal. 512 bytes in decimal. In binary, that's 0 1 0 0 1 1 0 0 1 0 0 0 0 0 0 0 0 0 divided by decimal 3. That will give you 512 divided by 3 decimal. In binary, that's 170 in decimal. In binary, that's 0. In decimal, that will be, so you get 512 divided by 3, which is 1 0. Okay. 1 0 1 0 1 0. So the first problem that's here is two homogeneous transistors can fail. So the transistor can just bind on one or two. So it's not really it's really a medium more problem, but it's basically the first one I want to say for data is dynamic programming. This can be resolved dynamically. The number is 17 over a range of values. But let's stick with 1 0 1 0 1 0 1 0 from the right side or right NDS model for 170. 170. This number is 170. 170. 412 divided by 3 is 170 in binary. In decimal. And then you get in decimal is 10 10 10 10, and that's 170 in decimal for 3 packets. Now the bipolar will be the bipolar will go through the process of using repair, creating the message. When this is created and it's chaos, see something what goes wrong, it will start to bring it. So if it gets to chaos, you can compute ahead of time for the opposite of destruction. So let's say the message start to destroy somewhere. The message is OB nexus, OBR nexus, which is 512 bytes long. But OB nexus, and this will, so we get we get some malformed characters here. We get U, actually. So we get this is OB nexus. We get O and OR. We get some corrupted OI for BI. And then we get N. We get empty. We get empty epsilon, which I'll put cross into for empty because epsilon is just look at the E. So I'll cross the epsilon, OI epsilon, or come to the and then we get OI epsilon for nothing, and we'll get data for N, because data is in the message schema as well, for yes, no, and maybe. And we get epsilon again, and we'll get one more epsilon, and we get we get one more epsilon, we get x, we get x, we get x we get x as it is, and we get u and s. So the system here, so we got data. So this is how the message packet works. So you get the problem is dynamic programming. First of all, that's the first problem. Can we get 170? Yes, in the range of values that's equal to 1/200. And just look that up as a result. But the problem here mainly is this problem here. So we got we got O. Which we said was O. We get B, we get I, but I is basically the wrong message. So how can we check if I is B is not I? My B is your I, because you send back an I. This means you send back an I. OB I. So you send back an I, that means the message is wrong. The wrong. So you send back. So I sent OB nexus. I sent O for Oscar, B for Bravo, I for India, N for November, E for Echo, X for X-ray, U for Umbrella, S for Sarah. OB nexus. You send me O for India, I for Indigo, epsilon, data, epsilon, X, U, S, X for X-ray, U for Umbrella, S for Sarah. So you can check that O, X, and U, S are fine, but why do we have I when I have O, B? This is basically the problem of inverse polar systems. So that's why this is what the problem matters. So the solution is dynamic programming to search on the table. Yes, and the table is there for OB nexus. So we'll say so we get B, we get I, and that I is epsilon. I is my, so your I is my B. So you're giving me your I, and this message is not right message. So I'm trying to verify the message too. So I have used the order collection frame. So I have to either renew your bean. So I have a function that renews. So I created a method, I built it, I have repaired it, and I renew it. So you have now found that I can destroy it, build, break it, and repair it. So just 4 operations, 4 functions that map to this problem of this problem here. So all is fine. All is fine. I verified, I didn't need to send all again. But now to send okay, send the whole message back. Did you send me? I said, so I don't need to touch, or I need to touch, I need to tamper with the message. Oh, you send me I checked this, your B is my I, so I have to give you my B. So I have to shuffle again. So I have to say, I'll give you, so you gave me index O, B, I. Your index, my index 0, 0, 1, 1, 2, 2. I should give you 2, my index 2. I give you my index 2. So I either give you my index 2, or this is my give you my index, so I should give you index 1, 1. And that will be B. Because it will share as B, 1, 1. And then we get epsilon. Now, epsilon is n, but n is empty. So what does epsilon mean? So you have to look at the state. And this is really a valid message here that can be corrupted here. It can be valid corrupted result. Epsilon will be like an empty message for I. Because I came from this one here, so it may have shifted because it didn't give me beam. So I'm saying to this I is more it's more humane. It's more like the system made a mistake. So and this I'm doing guys with this message here, making it look a real rife. So so you give me epsilon. Epsilon here. What does epsilon mean? Epsilon means nothing. You give me, so you get this epsilon, you can use epsilon, you give me your epsilon. Now, as you use epsilon is a slash, that is your epsilon. It's basically an E with a slash, but my epsilon will look at me, so my tomorrow will look at an epsilon sign, but look at you, this is your epsilon. So you give me your epsilon, you don't know what this is, you don't know what this I is. So I'm telling you, you don't know what this, so I have to replace it. So I have to what? Renew it. So I have to give you I. And I have to give you index 1, 1, 1, 1, and index 2, 2. And a theta, you're sure what this n is. So you are thinking it's either n. So I have to now renew the n. So the n will be index 3, 3. This means going forward and 7. So index 3, 3. Or your question is because it's on ground. It's normally it'll be an alphabet, or the polar inverse will be -1, and it'll be -3 and 3. So I can give you -3 in your frame, negative number. So it works like that. So I can give you -3 and 3. -3. What is -3? So I give you the opposite. You don't know what that is. So I give you -3 and 3. So I give you 2 packets maximum. So 3, 3, or -3 and -3 and -3. For -3 and -3, or 3 and -3. I give 3 messages maximum. 2 at a time, of course, depending on the kind of order you're on. And you get XUS as always. So the message now, so there's no negative here. So you get 3 or 3, or you get the polar inverse, which is B negative. So you are working on the negative. You're working negative. So you're working on the polar inverse will be -3 because you're working on an operator from the right side. So the right side will be basically because you're doing right side operation, or will be XOR, which means like XOR operation that will save the byte of the data. But the English byte will be XOR or minus XOR. So you're giving me your minus exclusive operator that works on that remembers the state of the XOR. So it's basically a negative operator, something on the computer's one for the structure. So if the XOR operates the structure, the polar inverse will operate on the right hand. The minus will be the right hand NDS or the left hand NDS of the ecosystem, and that's how the system works. So the message in the end will be verified ahead of time via Spring physics. Spring says double time. So I send this message. I see 3. I see 2. So I give you 2. So the result will be the system will be 1, 1, 2, 2, -3, -3. Because it's -3, because you get -1. This is -3 because there's chaos. Because you don't know what this will be, I give you -3 and 3 and 3 because this is a 3 will give you 1, 2, 3, 4. 1, 2, 3. Will give you maybe, give you the result of the data. And data will be it's either -3 or 3 based on the axis of model of the axis I'm working on. Because this is index negative, so you get once you get OBIN, OBIN, and the N will be the negative third index, depending on the XOR operator you're working on. So how the XOR operator works is just the last part of it. Because in the meantime, just remember the system of XOR. The system is an operator, but they are working on poles. So if you get a negative X, you get a positive side. If you get a positive side, you get a negative side. And that's what the poles do. But they work on multiplication because they work they're dynamic. So they work on multiplication. So they work on kind of a system of multipliers and addition and scalability because the spread this work. So let me roll this out and show you the final solution for the system. So the final solution will be we use this diagram. So the final system, all the system will be the X operator will be operating on the inverse. So if I have if I didn't have this is ASCII systems. So if I now convert this to O to binary ASCII, OBI next is ASCII. Let me just get this let me just a good quick ASCII converter. ASCII converter. ASCII converter. ASCII says OBI. I'm busy. Yeah, how are you, mate?
Alright.
Yeah, I'm good. ASCII solution to basic the form. OBI nexus ASCII says. OBI nexus in capitals will be. So if I see the binary equivalent of OBI nexus, I will just have the hexadecimal with the hexadecimal the byte. So if I use the hexadecimal in bytes, so that'll be 42 4F. 4F. So we have XOR. So we get a table of here 4F 42 49 no. So I have to do the message. So the message here is so we have to take whatever the system was. So that will be 42. Which is so you get the message. So you get the two messages. You have to have OB nexus and the malformed messages to work. So that's what I'm doing now. I'm writing now in hexadecimal digits. 4A. So the first three parts of epsilon. So OI. So you get 49 here. So 49. I'll get I. OBI. O is 4F. 4F is 4F. Well, 4F. So we get 4F. We don't change that, we get X or 4F. So we get X 4F, which is equal to 4F in the long run, which is O exclusive O, which would be 1. So the message would be 1, because you don't exclude. So that'd be 4F, which would be 1, which would be 1, which would be 4F at the end. Now we get 42 XO 42 or 49. So I'm going to preserve the 42. So the 42 will be the original message. B. 42 is hexadecimal. That'll be 42 in hexadecimal, which should be so I'm trying to do 42 or priority or 0. So I have to get 42. So I have to use the self-balancing tree model of the system again. So that will be so I'm getting so I was going to be 42, and I've changed it, I've reorganized it. So I've gotten so I think this will be 2 2 2 2 2 2 0 1 0 1. This would be 1 1. So I have to use the indexing of 1 1. This is of 1. This is 0 1. No, this is of 0 1 2 2. I have to change the index 2 2 to 1 1. And that will give me B 2 2 to 1 1. And that will be the index 2 2 to 1 1. So that will be index 2 2 to 1 1. And that will be the correct input. So 2 2 to 1 1 will be 2 2 to 1 1 will be B B B B B. And that will be the message I was. So this offer. So O B or I should get B, but index B will be I. Because in fact this is not so I'm trying to remember I. So I've used index 1. So what's the reverse index? What's the change in index to 2 2? I didn't apply the XOR operator again. Or I can do the XOR operator for your table from your table or my table, based on your table what you saw. So I'm going to give you the index 1 1 again, and that will be 1 1. That will be O. So XOR will be so this one should be verified here. This one should be verified here. But I actually compute. Basically, when you verify the message over OK or XOR operator, you're getting another message, a parity message. The parity sequence will give you the result you need. So that is basically what you change for that message. And that's how that works. So you have OBI, O is fine, B is not fine. So I have to change index 2 2 to 1 1. And that's verified. So now that will be 1 1. And now I have data and epsilon. Epsilon will be either I. Actually, it's nothing. No, nothing. So you don't know what this is. So I would say I'll give you 49. 49. I'll give you 49 because you only so I can change it up to 49. So you have 49 via the XOR operator. So now I get this becomes I. Now this becomes I. So I give you I because you don't know what this is. I give you data. Data. Data is basically you're sure what this is. This is an N. N, what this N can be, if you're balanced, so N will be NE or N or I. So my N can be your I, no, your I. If you listen, my N can be your no, my N can be your E. My N is your E. My E is your X. And my X is your S. As you can see, so if I'm giving you an N, you don't know what it is yours, I'm giving this an E or an X. So I'll give you I have to shift your view. So I have to change the dimension. So I have to just give you my table. So I have to give you 2 halves left, give you the direction. So I have to give you 2 halves left. So if you're thinking this is S, this is one table share, one alphabet will share, you're thinking that this one is encoded, this is how it's encoded. So this either be negative or positive, but I'll give you data, and data will be XUS. So I'll give you shift the view -1, -2. Diameter course view -2. So as you can see, I got N to November, which is same as E, X and then E for X for X and X for X S S U. So you think it's I don't think I'm giving I. You're not thinking I'm giving you an I'm giving you an I, O, and B. But you're not sure where that lies. So you can say this is something you said. So I can switch to the pole. So the pole will be X or 5. So you start with the X. So I'm giving you a maybe. So maybe it's N. Well, maybe it's N. Well, maybe it's M. Maybe it's something close to M, which is M. Will be so you think it's either E, I, or M. You think it's either E, I, or E, I, or I, N, E. So this would be N. Sorry, this would be N E N E N E I. INE, which is like on the root left right, depending on what's the root. So I'm giving you an N, so you don't know where to start from because you don't know where you are at. So I will construct the table. I is on the right, left. I is on the right. N is on the root, and E is on the right, left. And I'll give you what it is. So I can give you this table to look up. I can give you this whole table to look it up. But I can just give you the answer. So I'll give you the whole substruct of the table. And that will be NIUM. So that will be I and E. So INE will be the Cisco model of INE. So this INE will be the one of the, so I'm giving you an I, you give me an I. So what is this M? M will just result to this M. And that M will be something that N, because you know this M, so that would be maybe, so it's basically what's on the table again. So let me write this. So what is the N on the table between I and E? I'm gonna give you the midway, the middle. If I go to OB axis, which is on X and the Y axis, OB nexus, which is on X and Y axis, where is M? Where is N if you have an OBI nexus? BB, so NE will be here. So here we have so as you can see here, I have IM, EM, and I have EM, I mean EI, and EM. So this basically was, so I'm going to find the M. So you don't know what it can be anything in this set or everything. We're going to reduce it to anything in this set. So anything in this set will be NM. So that will be index 1, index 1, 2, 3, 1, 2, 1, 2, 1, 2, 1, 2, 3. So look for number 3, 3. 3, so negative 3. So if you got 3, you got negative 3. So whatever the I is. So if I'm an II, I have to move one row. So if I'm an II, so one II index I'll have to move one right, one right, one right, and one down, to get NM. If I so I have to use one right, one down, one down. It's always an up, down, left, right. Basically, the axis of robot, which is really actually depending if I start on X on Y to X. So if I start from the Y to X execution order, I used to use one right, which is II. I used to go one right, one down to get to NM. One down, one down the axis of the y-axis. So one right on the x-axis, one down. And if I go, if I start from one right to get y-x, to get one m. If I start from one m, I get one down, one down. So depending if the message is maybe, then maybe you can use the subset. So this basically can be in anything of the subset or everything, but the subset is basically one maps to one up, one down. So this is a table. You look up a table. So I give a sequence of instructions that can resolve the system based on whatever the current set was. So you can test some more. So I'll now show you the yes, no, or maybe. So the message is now incomplete, but I've got less time to do it. So I'm showing you, you have to take some go with it. So so because the table is what you're gonna compute ahead of time. Not ahead of time. Why people is right? It's not ahead of time computation here, because you don't need it to do it. So you get one right, one down, one for II, and you get one right, 1 down for II. And you get for II 1, 1, 1 down for IN, and you get 1 for EI. For EI, you get 1 left axis rotation, 1 left axis, which is not 1 rotation of the axis. Because you can change it as Q. One, I'm just leading. You can do rotation. You can do also transformations. You can do standard rotation. You get rotation of the axis. Rotation reflection, rotation reflection of the axis based on theta being to observe based on the part the 2 pi r to 1. I mean 1 to 2 pi r. One full message to 2 pi r, which is basically the parameters of travel. And you get 2 pi r to 360 to pi r squared, which is the area of search space. So pi r squared is the search space. And how you do this mathematically is you have to verify that you're searching the right space based on the dimensions of the problem you're working on. Because basically a color you can have some. I'm going to have a implementation where the hexagon canvas is used to have this as a ball of ASCII characters. But I'm going to show you the video later. So I'm going to have a ball of ASCII characters on the HTML5 canvas to show the SIGII protocol working via trident ruling. Ruling means the final vector. Ruling means command and control sequence. So there's no spoofing involved here, but you have to show that it works as intended. So the sequence equation have to resolve the system. So again, you have yx which should be the anything and not everything. EI, which should be -1 e, minus one left, minus one left, axis shift, and then minus 1 down, which should be NM. And you have to see all the messages rotate and point to the NM, which should mean N nexus. So that'll be the N for nexus. So the message will prepare O for Oscar, B for Bravo, I for India, and N for November. Same. E for Echo, S for Israel. Okay, guys, thank you for watching, and that's how the work. Here, EXO. The EXO remembers the state of the current state of the stale. It's a stateless system. Stale. That means it knows the state. It's still. It remembers what is done. It is still. It remembers. And there's no forget. It never forgets the protocol, and it doesn't forget. So the next video will be on the HTML5 canvas. But with still protocol. It's not stateless. Yes, but remember it's still the state. It's stateless. Doesn't mean it doesn't remember. But it's stateless. It remembers stuff. It doesn't need to forget ever again. So it encodes that into the geometry of the system, so you can add new character sets as language evolves. Thank you guys for watching this video. Have a lovely day. My name is Namdi, and take care if you're enjoying it.